So this is how we left the previous video, and we were talking about Avery and the importance of his discovery. What did he do in the laboratory to actually make him make this statement that says DNA is the material that makes genes and chromosomes? Very profound statement, very important statement, very stapled now within the world of DNA. But again, no Nobel Prize was given. Kind of depressing in a way. That's like coming up with the cure for cancer but not getting any credit for it. That's like coming up with the medicine that will treat male pattern baldness but never receiving a dollar for your discovery. Poor Avery. So, what goes on in the laboratory during the time? I mean, how did they determine that DNA really is what made up these chromosomes and genes? Okay, well, we've got to bring into the discussion a poor little rat. Um, Poor little rats, actually. Hundreds of rats, all sacrificing their life in the name of science. Poor little rat. I kind of feel sorry for them sometimes, but without these rats making a devotion to science the way that they do, we really don't receive some of the discoveries that happen in the laboratory at all. And during the time, what began to happen is that they took lab mice and they injected them with what we call a rough strain. And that's what you're seeing here in the first column. So a rough strain means non-virulent. So that means it doesn't carry a virus. It's just kind of a placebo effect in a way, or if you want to think of it, it's a virus that is dead. And they inject this dead virus into this poor little rat, and then they just kind of sit back and wait. And over a course of time, the rat never gets sick. But that's not surprising, because we knew that the virus was dead. We knew that when we injected it, it wasn't going to catch anything, and it shouldn't have caught anything, and it should still be healthy. So this rat survives. Yay! And then it goes off and it hops and it plays on the wheel, and then, it eats and drinks a little bit, and then it probably dies in a couple of weeks. But, at least for now, it's safe and sound. Okay, in the next round, what we see is something called a smooth strain. And this is virulent, meaning it does carry a live virus. So we have this live virus in a syringe and a needle, and we inject the mouse with this live virus, and we know that it's a live virus, and we know that there's probably no chance for this rat to survive the virus and the infection, and then that poor little rat dies. So they turn it upside down and they draw it gray on your screen. Poor little rat. He didn't ask for that. We did it to him anyway. Okay, so again, not surprising. We knew it was a live virus. We injected it. We knew the mouse was going to get the virus, and we knew that the virus was going to kill it. Okay, so number one, number two, not surprising. And then what we do is that we have this thing called heat-killed smooth strain. So we take the smooth strain, which is the live virus, and we put some heat on it. And when we heat it up, this destroys the virus. It kills it. And then we inject it into the mouse. And because the virus is dead, well, the dead virus goes into the mouse, and the mouse fights off the infection without a problem, and the mouse survives. Yay! So he can go play with his buddy from column number 1. And then finally, in the fourth column, what we see is a rough strain and a heat-killed strain. Now pay attention. The rough strain was basically non-virulent. It did not carry a virus. These were just, you could think of them as cells that had nothing in them at all virus related. And then the heat-killed smooth strain. This was virulent at one point, and we put heat on it and we killed them. And then we mix these two things together. And this is where the surprising moment happens. Because we take these cells that are alive, that do not carry a virus, and then we take these cells that basically have a dead virus in them, and we mix them together, and we inject it into the rat. And the rat should survive. There's no virus there. We have healthy, good cells that are non-virulent, and then we have bad virus that has been killed. And this rat should live. The problem is that every time they injected this mixture in a rat, it croaked. And then they scratch their heads and they wonder, what on earth could really cause this to happen? Why is it that when we take these cells that do not have a virus in them at all, and then we take the virus but it's been heat killed, and we've already shown that a heat killed virus, well, the rat survives. Why is it that when we take these two and we mix them together, the rat actually croaks? And this is where Avery makes the discovery. And they determine at that time that something is happening here. These live cells that did not have a virus, non-virulent, these live cells must have somehow caught the virus. And because of that, we got an active virus that we injected into the rat. So we've got this virus that's been killed by heat, so they become inactive. There's got to be something in that virus that transfers out of those dead bodies, in a way, and into the alive ones. It is like a zombie apocalypse, right? We see these things that are carrying the virus and they are dead. And then we get an infection that spreads, and now all of a sudden this person that was living is now a zombie. That's exactly what's happening here. So we have this material that has left the virus and has transported itself and transplanted itself into these non-virulent cells and made a new virus. The infection is beginning all over again. And these live cells now are infected. And these infected cells become the virus that we had in the beginning, and now it makes our poor little mice die. So this whole transfer aspect is something very important. This is how disease spreads. This is how it gets worse, right? Healthy cells get infected. Not only that, but what's on the inside of this virus to make it up? What's actually getting transferred from one to the other? That's something that we have to talk about as well. But this is our first step in the direction of realizing that maybe, just maybe, it's not really proteins and amino acids that are doing the job here. It's actually something else. Okay, so this whole term of smooth that we saw in the previous slide, well, this kind of explains the concept of what smooth means. It actually talks about the surface of the polysaccharide capsule. So these things are made up of a multiple sugar compound, polysaccharide, right? And smooth colonies have a polysaccharide capsule that what we call includes antibody formation. So, kill the bacteria with heat, extract the saline-soluble compounds. That just means salt, saline, kind of salt, like saline solution that you use for your contacts. Protein was precipitated out using chloroform. So chloroform the solution, you get protein that precipitates out. We get this polysaccharide that is basically making up this capsule. And we want to get rid of the polysaccharide, so we throw in an enzyme that hydrolyzes it. It breaks it all up into the individual sugars. We then throw in alcohol and we fractionate the solution at that point, and we remove what we call the active portion, which results in fibrous strands that can be picked up with a stirring rod. We then take this fibrous strand and we do an elemental composition on it. And it shows that the percent composition of that strand is proportionate to what we are now calling DNA. We take DNA and we throw it into a test tube, and we put trypsin and chymotrypsin and some of the other enzymes that we talked about in the amino acid chapter, and this did not break anything up. It didn't break anything apart. And this was a good sign because this proves that this stuff, this strand, was not made up of any proteins or any amino acids. So it rules out the fact that this stuff that I'm ending up with has some protein and amino acid in it. It is a completely different type of family. So this is the process that we isolate DNA. And the concept still exists in the laboratory today. We can take your cheek cells and we can isolate those cells, and we can shock them with some salt water, and we can burst those cells up, and we can hopefully release some of that DNA material in those cells using a little bit of alcohol, a little bit of detergent, a little bit of salt, and we can extract this fibrous strand that you can actually see with your human eye. I can do it with cheek cells, and I can do it with strawberries. I can take strawberries in the lab, crush them up, put a little bit of salt water, a little bit of detergent in them, and I can do some magic to it, and then I can pull out DNA from a strawberry. The same exact way. That's how we did it now, and do it now. That's how they did it back in the day. But this purpose of trypsin and chymotrypsin proves that no protein remnants were left behind. So this means that this stuff that I've isolated, it's not a carbohydrate, it's not a lipid, it's not an amino acid, and it's not a protein. This is something different. And we regard that stuff that's different today as DNA. Okay, so I'm going to stop the video here. We're going to come back and we're going to continue this discussion about the discovery of DNA in our next video. And again, we're kind of we're just getting acquainted with everything. That's all that we're doing. We'll take a look at structures and that kind of thing a little bit later. We're just getting ourselves acquainted with the whole field. It is a fairly new field. You're looking at these, and these are early 1900s here. So, fairly new field, fairly new information. But we have came so far since the discovery of the DNA that we can just imagine the possibilities that it continue on. So in the next video, we'll keep trucking along with the story. Hopefully you don't regard this as a bedtime story and fall asleep during it, but we'll continue on with the story in the next video.